All right, today what we're looking at is erosion. We're looking at erosion. All right, so as you mentioned before, people a lot of times get erosion and weathering mixed up. They're two processes that frequently go hand in hand, but they're two very different processes. Now, what we said with weathering, we said weathering is basically the process in which rocks break from big pieces to little pieces, right? Erosion is a process where material is moving from one location to another. So the reason why these two processes go hand in hand is that it's a lot easier to move small particles than it is big particles. So if I had this big giant boulder that was 30 feet across, it's probably not going to move very easily, all right? However, if that big giant boulder were to undergo weathering and break into a bunch of little pieces, then those little pieces could move pretty easily. So that's why weathering and erosion go hand in hand, because it's a lot easier to move the small pieces you get after weathering than it is the big pieces that you start off with. All right. Now, evidence that erosion has taken place. Well, perhaps the best evidence that erosion has taken place is when you find displaced sediments. Right? So, for example, right, this rock right here. All right, this rock right here, you may recognize this. They make countertops out of this. Here's a piece of granite. All right. Now, if you were digging, let's say you're digging a hole in your backyard, plant a tree or something like that, and you're doing it in upstate New York, and you're digging a hole, you very well may come across a piece of granite, and you may not think anything of it, but there is a significance to it, and the significance to it is granite does not match the surroundings. So like where we live here, Phelps and Clifton Springs, most of the bedrock around here are things like shale and sandstone and limestone. Those are rocks that originally formed in the ocean. Granite is an igneous rock. That's a rock that formed from the cooling and hardening of magma. All right, so that did not form around here. It doesn't match the surrounding bedrock. So what that tells us then is that rock must have came from someplace else and got moved and transported here. So when you find sediment, when you find material that doesn't match the surroundings, that's a clue that erosion has taken place and those particles have moved from one location to another. All right. Now, things that you need for erosion to take place. Well, first off, you need something to be eroded. You need some sediment or you need some material of some sort. You need particles that are going to move. Two, you need something to move those particles. And the things that move the particles we refer to as agents of erosion. All right. So like the water flowing in a stream can move the sediment, or ice in a glacier. As the glacier moves, it can move the sediment. Or as the wind blows, it can blow the particles around. So the things causing the material to move, we call the agents of erosion. Right? Now, something has to make these things move, right? Just a glass of water is not going to cause any erosion. You need moving water, you need moving ice, you need moving air, right? Now, the force that makes this stuff move, the driving force for erosion, is gravity, because it's the water flowing down a stream or down a river. The reason why that water is flowing down a river is because of the force of gravity. With ice and glaciers, the reason why glaciers move is because they're basically moving downhill just like water does because of gravity. Wind, it's a little bit more complicated. Basically, you have different areas, different densities, and stuff like that, because of differences in heating in most cases. But again, what's making the air move from one place to another, again, is gravity. All right. So gravity is the driving force that makes the agents of erosion like water, ice, and wind move that can take sediments with it. That's how you get erosion take place. All right, now we're going to look at each one of these agents of erosion in a little bit more detail here. Some of the characteristics that they leave behind and so forth. So first off, stream erosion. Now, particles that have been eroded by streams or particles that have been eroded by moving water are pretty distinctive in that when you look at them, what you'll find is you'll find material or particles that are very well rounded and quite smooth, right? Like this rock right here was one that was transported by moving water. Now I know that because I found this in a stream when I was fishing. Right? So see how it's nice and smooth, rounded like that? So that should tell you right off the bat that this was eroded by water. So you'll find rocks like this in streams and rivers. You can also find rocks that are smooth and well rounded like that at the beach sometimes too. Even though it's not a river, the waves and stuff at the beach are moving water. So they'll make things like pebbles and stuff at the beach nice and well rounded too. On a larger scale, what stream erosion does to the landscapes, stream erosion carves out valleys that have V shapes to them. We'll talk more about how streams and stuff affect the landscape in more detail another day. All right, now there's different ways in which streams can carry material. Different ways it can carry material: suspension, rolling and bouncing, and solution. Now, if you've ever seen a stream after you've had a rainstorm, what you'll notice quite often is that the stream looks very, very muddy. All right. The reason why the stream looks muddy is because the stream is carrying a lot of particles in suspension. Suspension means there's basically a bunch of little particles that are kind of like floating in the water. All right. Now, the particles that are kind of floating in the water, suspended in the water, are going to be fairly small particles. All right. They're going to be usually pretty small particles. But the faster the water's going, the more different sized particles it can carry. So a fast moving stream can have more particles in suspension than a slow moving stream. All right. So very small particles can be carried in suspension. Now, bigger particles can still be moved by the stream, but the water might not actually pick them up. So like this rock right there, right? If this was the bottom of the stream and the water was moving that way, the water probably would not pick up the rock and carry it like that. But what it could do is it could still move it. If the water was moving like that, what it could do is kind of push the rock and maybe roll it like that along the bottom of the stream. Or if the water was going maybe a little bit faster, what it could do is kind of bounce along the bottom. So rolling and bouncing is how larger particles get moved. Because a lot of times you might see rocks that are like this big moved by a fast moving stream or a fast moving river. Rocks that big, the water didn't pick up and move in suspension. It just kind of pushed or rolled them along the bottom. Now solution, that would be like a rock salt. If I had like a shovel full of rock salt and I put it in a stream, what you would notice is that as a little time went by, the rock salt would dissolve. It would chemically become part of the water, and then wherever the water moved, it would take that material with it, as part of the water. Right? So solution is stuff that's dissolved in the water. So 3 ways which stream could transport material: suspension, rolling and bouncing for the larger, suspension for small particles, rolling and bouncing for the larger particles, and solution for stuff that's dissolved. Now, the main thing that determines how much material is going to be carried, or the size of material is going to be carried, is how fast the stream going. So the stream velocity affects what size particles the stream can carry. So there's a few things that affect that. One is the slope of the stream. So let's say there was one stream with a profile like that, another stream with a profile like that, all right? So the water's flowing like that, and this one the water's flowing like that. All right? And they both have, say, the same amount of water flowing through them. All right? Well, this one right here, the water is going to travel faster than that one right there because it has a steeper slope. All right? So that's going to result in a faster velocity. Now, the significance of that, the greater the slope, the higher the velocity. Higher velocity equals more erosion. So the faster stream's going, the more erosion takes place. So the steeper it is, the faster it's going. So the steeper it is, you're more likely going to get more erosion. Now, you don't normally see a lot of streams that are at an angle like that. If it was that steep, what you're more likely going to see is maybe a bunch of waterfalls like that. But still, overall, that has a pretty steep slope there. So that would still result in a lot of erosion taking place. So wherever there's a waterfall, there's a big difference in elevation. So like Niagara Falls, there's a lot of erosion taking place there, for example. All right, another thing that can affect how much water is going or how fast the stream is going is the discharge. Now remember what discharge is, that's how much water is flowing through the stream. The greater the discharge, the higher the velocity. The more water flows through the stream, the faster it's going. And the faster it's going, the more erosion takes place. So like after a heavy rainfall, where there's lots of runoff, and it'll make the level of the stream goes up, and there'll be more water flowing through the stream. It's gonna be going faster, and as a result, you're gonna get more erosion. Most erosion takes place just a few days of the year when the level of the stream or river gets up really high. That's when you're gonna have lots of erosion. In the summertime when the stream levels are low, there's very little erosion takes place then. Now another thing that can affect the speed of the stream is where you are in the stream. So let's say I have a stream channel. It looks like that. All right. Now, first off, in the straightaway right here, right here in the straightaway, if I was going to do a cross section of the stream, so this would be a cross section of what's going on right there. If I do a cross section of the stream, the water is not traveling the same speed throughout, right? So first off, where it's going to go faster in the middle or towards the sides is it would go faster in the middle. And the reason why it's going to go faster in the middle is because when the water comes in contact with the ground, there's friction there, and it basically acts like a brake slowing down the water. So all throughout here, when you're near the ground, it's going to slow it down. So it's going to be faster towards the middle because it's away from the ground. The other thing is, whereas we're going to be faster towards the bottom or near the top, it's going to be faster near the top because, again, near the bottom, the friction with the ground is going to act like a brake slowing it down. So in a profile of the stream in the straightaway, it's going to go fastest in the middle towards the top. So if I was looking down on it, you go fastest in the middle and then slower on the edges like that. Okay. Now, when the water goes around a bend, that changes. When the water goes around a bend, it's kind of like, if you've ever seen like those couple skates for roller skating or ice skating, you're skating hand in hand with someone, and then when you go around the bend, what you'll notice is the person on the outside gets whipped around and goes a lot faster. Same idea here. When the water goes around a bend, it's going to go faster on the outside of the bend and slower on the inside of the bend. So because it goes faster on the outside of the bend, you're going to get more erosion. Right? Just like right here. Now it's going around the bend this way. the outside of the bend. It's going to go faster on the outside of the bend. So right here, you're going to get more erosion. And then when it goes the straightaway again, it's going to be fastest in the middle and then slower on the sides. Okay. So normally it's fastest in the middle, but when it's going around a bend, it's faster on the outside of bends. And quite frequently on the outside of bend, if you ever gone fishing or anything like that, you notice on the outside of the bend, there's usually a deeper hole because the fast moving water erodes more, so there's usually a deep hole there. On the inside of the bend, it's fairly shallow because you don't have much erosion there. All right. Now, there's a chart in your reference tables that shows you what effect velocity has on the size of particles. And it is on page 6 of your reference tables. All right, so this chart here on page 6 of your reference tables, it says relationship of transported particle size to water velocity. So basically it shows you how fast a stream has to go to carry certain size particles. All right, so before we, let's look at the axes of this. Down here you got the stream velocity in centimeters per second. Right here you got the particle diameter. All right. Now, before we do anything with this, over on the side of the map over here, there's an important part of the chart that shows you the exact dimensions of different sized particles. So, for example, for a piece of sediment to be a pebble, it would have to be someplace between 0.2 centimeters to 6.4 centimeters across. So if I had a rock and I measured it and it was 4 centimeters across, that'd be in between and that'd be a pebble. If I had a rock and I measured it and it was like 12 centimeters across, well, from 6.4 to 25.6 centimeters, that would be a cobble. Anything bigger than 25.6 centimeters would be a boulder. From there to there is sand, from there to there is silt, and then the smallest particle there on that chart is clay. So here it gives you the cutoff points for the various sizes of particles. On this side of the chart here, it shows you the particle diameters. So it kind of matches up with that there. Now this is probably a little different than a lot of the charts that you've looked at before, and this is what's called a logarithmic chart. And what that means is this doesn't just go up like 1, 2, 3, 4, 5. It kind of goes up by factors of 10. And what I mean by that is there's 0.1, that line there is 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9, 1. But that next line is not 1.1. That next line is 2, 3, 4, 5, 6, 7, 8, 9, 10. All right. Now that next line is not 11. That next line is 20, 30, 40, 50, 60, 70, 80, 90, 100. So it goes up by a factor 10 each time it goes like that. And the same thing holds true in the bottom. The bottom's a logarithmic scale as well. So like there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That line there is not 20. That line there is not 11. It's 20, 30, 40, 50, 60, 70, 80, 90, 100, 200, 300, 400, 500, 600, so forth like that. All right, so how you use this chart. Let's say I had a stream that was traveling 50 centimeters per second. And what I wanted to do is figure out what is the biggest particle it could carry if it was traveling 50 centimeters per second. So what I do is I come down here to 50 centimeters per second, and then I come straight up like that. That's going to bring me right to about there. So the biggest particle it could carry would be 1 centimeter across. All right? So a stream traveling 50 centimeters per second, the biggest particle it could carry is 1 centimeter across. Now, if I wanted to know the name of the biggest particle it could carry, then I'd come over here and I could see that when a stream's traveling 50 centimeters per second, the name of the biggest particle it could carry would be pebbles, would be the biggest particles it could carry. Or another possible question you might get. If a stream was, if a sediment was 10 centimeters across, how fast would a stream have to go to move that? All right. Well, there's 10 centimeters right there. All right. So if I want to find out how fast a stream has to go to move that, I go over like this until I hit that line, and then I come down like this. So that puts me right about at that line right there. There's 100, so that line right there would be the 200 line. So to carry a particle 10 centimeters across, so about that big, a stream would have to be traveling about 200 centimeters per second. All right. So that's how you use that chart. So how fast the stream's going, how big the particles are, then over here it shows you the names for the various particle sizes, how big a particle would have to be like a cobble or a boulder or something like that. All right, so that is stream erosion. Okay, next up, wind erosion, all right? Now, wind doesn't have as much force behind it as water does, so as a result, wind cannot pick up as larger particles. And in a lot of places, for example, upstate New York, we really don't notice wind erosion that much. And that doesn't mean it doesn't happen, we just don't notice it that much, and the reason being is we live in a humid climate that has lots of water, and moving water does a much better job of eroding than moving air, because it has more force behind it. So most of the features of erosion that we see are the results of moving water, not moving air. So any place that gets a fair amount of rain, you're probably going to find that to be the case. However, where you do see the effects of a lot of wind erosion is places where you don't have very much rainfall. So it's dominant in dry climates like deserts. In a desert where you don't have very much rain, then you're going to see more of the effects of wind erosion. There's a whole variety of special features that are the result of wind erosion that you wouldn't see if an area had lots of water in it. Now, if you take the particles that have been moved by wind and you look at them through a microscope, how they would look, they're going to be rounded, not as rounded as stream erosion, but they'll be somewhat rounded. They'll have a pitted look, so kind of like that, or a sandblasted look to them. Another thing that you might notice, it's not mentioned here, but if you look at it through a microscope, material transported by wind sometimes has a frosted look to it. So that means just kind of, what I mean by frosted look is like a glazed donut. It has kind of frosting on it. It kind of would look like a glazed donut at the surface of it. Okay. So that's wind erosion. Glacial erosion, right? Now, since ice is a solid, it can carry all different size particles, right? Because if I put, a pebble, if I hold a pebble out there and I let go of it, it's going to fall to the ground because the air can't hold it up. But if I put a pebble on top of a glacier, because ice is a solid, it's not going to fall through the glacier. So since glaciers are solids, they can carry all different sized particles. They can carry little tiny grains of sand. They can carry boulders that are 50 feet across. They can carry all different sized things. And they're all kind of mixed together. So they're all unsorted particles that are very common with glacial deposits. Now, so a feature that's commonly found on material that's been eroded by glaciers is a lot of times they'll have these parallel scratches on them called striations, right? So that represents right there. So how I get a striation, right? So let's say this blue tray right here is the bedrock, and this rock is just sitting on the bedrock like that, and there's a glacier on top of it. Now, glaciers can be hundreds of feet thick, thousands of feet thick in some cases. So there's a tremendous amount of ice sitting on top of this rock that's pushing down on this rock. Now, as that glacier moves, it's pushing down on this rock, and as the glacier moves, it's going to make this rock move along the bottom too. But because there's millions of tons of weight pressing down on it, it's going to really push it into the rock beneath it. And as the glacier moves, this rock moves, so it's going to kind of grind into the rock beneath it, and it's going to cause scratches, and the scratches are going to line up with the direction that the glacier's going. So like right here, the glacier is probably going like that. Right? So right here, here's a rock that exhibits striations on it right there. All right. So sometimes it could be on the rock itself. Another place where you can see it sometimes on bedrock. So here's a place, here's the bedrock near the Thousand Islands, New York. And you can see these parallel scratches in the bedrock right there. I put a picture of my foot right there so you can see roughly how big this is. But those parallel scratches are glacial striations. It tells me that the glacier was kind of moving like that across the land. So parallel scratches are a common feature with glacial erosion. Now, on a grander scale, whereas streams carve out V-shaped valleys, glaciers carve out U-shaped valleys. The Finger Lakes in New York, those are all U-shaped valleys carved out by glaciers where the bottom is filled in with water. But we'll talk more about the landscape stuff in another topic. All right, gravity erosion. All right. Now, sometimes gravity doesn't need an agent of erosion. Sometimes the gravity itself can skip the agent of erosion part and make the sediment move by its own. So if a rock's falling off a cliff, it's not the moving water that did that. Sometimes the gravity, maybe there's a little earthquake or something that, kind of jostled it, and then it just kind of followed down the cliff. Or an avalanche. A lot of times you think of avalanches, you think of snow avalanches, but there's also avalanches where rocks are kind of going down the side of a hill too. Now with rock falls and avalanches, how the particles transported by them look, they frequently have angular shape to them. And the reason being is these are fairly short events. And a rock falling off a cliff, how long does that last? A couple seconds maybe? Avalanche, maybe a couple minutes. There's an avalanche, and then the rocks get to the bottom and they stop. So as a result, the rocks really aren't banging into each other that often. All right. Whereas with the stream, all right, what will happen is, let's say I had a very angular particle like that. when there's a bunch of rocks banging into each other in a stream, what'll happen is the corners are the first parts to break off. So that would break off, then that would break off, and that would break off, and that would break off. All right, then the more it bang into each other, the more the corners would break off, 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 corners would break off. So as the corners break off, it gets rounder and rounder, but the rocks have to keep on banging into each other to make the corners break off. So it takes a long time of rocks banging into each other to bang off all those corners. Well, with an avalanche or a rock's falling off a cliff, they're only banging into each other a few times, so they're not really getting an opportunity to round the corners off. Right? So material carried by gravity erosion, like rock falls and avalanches, are typically very sharp and angular in shape. Now, not all gravity erosion is fast. There is slow gravity erosion as well. And slow gravity erosion, soil creep or mass movement, that's where I have material that is slowly going down the sides of a hill. So sometimes you may see it where there might be a cemetery, a really old cemetery, that's on kind of a slope. And if you look at the old gravestones may be tilted like that. Now those old gravestones, when they buried the guy, they weren't tilted like that. They were straight up and down. But what's happened over time is the soil has slowly moved downhill like this. And as a result, it's causing the gravestones to tilt like that. Or another case where you can see this take place is with tree trunks. If there's a side of the hill, sometimes you may see tree trunks where the tree trunk is kind of like that, right? Now, when the tree would first start growing, the tree didn't start growing sideways. What happened is this part here was initially straight up and down because trees basically grow upwards towards the sun. But what happened is as time went by and the soil was slowly moving downhill, that was causing the trunk of the tree to bend over like that. And the reason why it has a bend like that is because the tree, as the newer parts of the tree were growing, it kept trying to grow towards the sun. So it was bending and adjusting so it would still keep on going up. So this part right here was straight up and down at one point, but the mass, the soil gradually moving downhill, turned it sideways, and then the tree was adjusting as a result. So that's frequently a sign that the material was moving downhill as well. Now lastly, a lot of times if you have property, you don't want your property to get eroded away. You don't want to lose your property. So there's some common things that can be done to control the erosion. One of the things is by using plants. All right, plants help slow erosion. Typically in forested areas, you don't have that much erosion. And the reason being is plants' roots and tree roots do a really good job of holding the soil together. Farm fields, on the other hand, where you're going to have lots of open field, where after they've recently plowed a field, in most cases, you're going to have lots of dirt on the surface that's not being held together by plants. If you get a heavy rainstorm, you're going to have lots of soil and stuff washed away. You're going to have lots of erosion. So forested areas don't have very much erosion, but places that have been clear cut get more erosion. And again, the reason being is the little roots hold the soil together. A lot of times on construction sites, let's say they shipped in a big giant mound of topsoil, but they might not need it for a couple months. What they'll do is they'll spray this green mixture of grass seed and fertilizer, and they'll spray that over the mound of topsoil. And the reason why they do that is the grass is a plant that grows very quickly, so it'll get its little roots down in the soil very fast, and it'll help prevent your mound of soil from blowing away or washing away if it rains. Or in yards and stuff like that too. A lot of times if they've redone the lawn and they've planted a bunch, or they put like new soil down so there's no plants or anything, they'll spray it with, again, this combination of fertilizer and grass seed, so the grass can start growing right away and it gets little roots down and it'll prevent the erosion. So plants help slow erosion. Another thing that helps slow erosion is large rocks. All right. So let's say there was a stream, and there was a stream like right here, and right next to the stream was a road like this. Now, remember that water travels faster on the outside of a bend. This is going to erode back. If nothing's done to prevent it, this is probably going to erode back and then undercut the highway right there. So obviously you don't want that to happen. So one of the things that's done to prevent that is a lot of times the highway department will get a whole bunch of big giant boulders, and they'll put a big giant boulders like that on the outside of a bend. All right? And the reason being is, if it's a big giant boulder, the stream's probably never going to go fast enough to be able to move those boulders. So what those big boulders are doing is preventing erosion, or at least slowing erosion down from going back and eating away the ground to the highway. So large boulders are frequently put on certain parts of streams where they don't want erosion to take place. Now sometimes instead of an actual boulder, they'll make like fake boulders, like they might make big giant blocks out of concrete or something like that. Or sometimes they'll take a bunch of smaller rocks and they'll kind of wrap them together with fencing to kind of create a big rock made out of a bunch of smaller rocks. And they'll put those on the outside of the bend because it'll basically act like a big rock. Another place you might see that with roads that are on a hill, if they've recently dug the ditches on either side of it, a lot of times they'll fill the ditches with big rocks. And the reason being is, if they're big rocks, the water can still flow through them because big rocks have a high permeability, but the moving water has a hard time moving the big rocks away. Right. So big rocks can be used to help slow erosion too. All right, so again, remember the difference between weathering and erosion. Weathering was when rocks break into little pieces. Erosion is when those pieces move from one location to another. It's easier to move small pieces than big pieces, so that's why weathering and erosion frequently go hand in hand.